What's going on, everybody? This is Mr. Diamond, and my camera is out of focus. So let's try to fix that. That seems like that's probably going to be a helpful thing to do. Let's turn off the autofocus. Let's get it good enough. Okay, what we're going to be doing in this video, as I remove the camera then to mess up the focus that I just worked so hard on. We're going to be doing examples of these three Ionic naming. And I'm going to talk a little bit about Ionic naming as well as we go through this. So the major idea and the major goal of what we're going to be doing is we're going to be taking these atoms individually, and we're going to, or these elements individually, and we're going to be trying to turn them into a compound. We're going to say what would happen if iron 3 and oxygen combined, or if barium and carbon, or if silver 1 and sulfate, or if calcium and phosphate combined together. So we're going to start with iron 3 and oxygen. With iron 3 and oxygen. So your first step that you want to do is first we have to figure out, well, what is iron 3? So iron is Fe. We know that from our periodic table. It is right here if you're having trouble finding it. So iron is Fe, and then this is a Roman numeral 3. Remember, Roman numerals only get used for this chunk, and this chunk of the table. And they are always used when something is positive. You can only be using Roman numerals on things that are positive and only for that limited area of the table. So iron 3 would be Fe with a 3 plus charge. Remember, it's kind of frustrating, but it's 3 plus and not plus 3. I'm not going to nitpick you, and I'm not going to count points off if you do it with a plus 3, though. All right, oxygen. Oxygen is right here. It is above and to the right. That means it's negative, and it is 2 steps away. So that means oxygen has a 2 minus charge. So we know what two pieces we're working with are, or what the two pieces we're working with are. The next step, and I'm going to switch to a pencil so it doesn't kind of bleed through as much for this next piece here. We're going to go ahead and do what is called crossing your charges. So to cross your charges, I'm going to write Fe. I'm going to write O, I'm going to write 3 plus, I'm going to write 2 minus, and then we are going to cross our charges. We're going to bring this 3 down to the O, and we're going to bring this 2 down to the Fe, and that's going to give us Fe2, because this 2 has gone down here, O3, because this 3 has gone here. Now, you might be wondering why we did that. This goes back to all ionic compounds are electrically neutral. We talked about in the notes video, which was the last video, and you should make sure you've watched that before you watch this because it'll help some of the pieces of understanding what's going on here. But in ionic compounds, they have to be electrically neutral, which means they have completely balanced out. The iron, in this case, has a plus 3 charge, and the oxygen has a minus 2 charge. We need to combine together some ratio of irons to oxygens so that they will completely cancel out. Now, you could do that mathematically by just trying to figure it out, and you could like add Fe's and add O's until they cancel. But the easiest way to do that is to cross your charges. Fe has a plus 3, O has a 2 minus, so we're going to bring this 2 here, we're going to bring this 3 here. And if you check, 2 Fe's would be 2 times a 3 plus, which is a 6 plus charge. And then O would be 3 times a 2 minus, which is a 6 minus charge. And notice that these two would cancel out, and you'd be left with something completely electrically neutral. You would have no charge whatsoever in that compound. So we would have, as our final answer, if iron 3 and oxygen combine, you would have Fe2O3. Now, to actually name this, we have 3 steps that we follow. First, we name the first element. So the first element in this case is iron. We leave a gap, and then we say, okay, well, we name the second element, but we change the ending to IDE if it's not a polyatomic. Since oxygen is not a polyatomic, we do have to change the end to an IDE. So oxygen becomes oxide. And then last step is if this was a transition metal or in the F block or in the lower portion of the P block, we have to add a Roman numeral because, again, we want our formula and our name to have every relevant piece of information. This formula tells us there are 2 Fe's, there are 3 O's. You can predict the charge of O because it's always 2 minus. That means you can predict the charge of Fe. Words or using words to represent a formula also needs to do the same thing. We know that oxygen is combining together with iron. Oxygen is always a 2 minus, but we don't have enough information with just this word to tell us what type of iron it is. So instead, we're going to also add in our Roman numeral 3. And I mentioned this in the other video, but just for reference, it goes 1, 2, 3, 4, 5, 6, and then if you went, it would be 7 would be an extra I, 8 would be an extra I, and we wouldn't really go anywhere beyond that. So iron 3 and oxygen combine, they would make Fe2O3, which is iron 3 oxide. Okay, let me try to get a little more comfy at my desk here. So we've got a couple more to go, and I don't want to get tired from doing this already. So let's try this. There we go. I know that looks like nothing changed for all of you, so I'm sorry. Okay, barium and carbon. Barium and carbon is our next example. Same thing as last time. We're going to go ahead and identify what both of these are. So barium is Ba, carbon is C. Barium is right here, so that's 1, 2 over, and it's below to the left, so it's going to be a +2 or a 2 plus charge. Carbon is right here, so it's above to the right, that's negative, and it's 1, 2, 3, 4, so it'll be 4 minus. So I switched last time because I wanted to make sure we had a little bit of easier time seeing what was going on to explain it. Now we're going to, and this is more work than you'd have to show on a worksheet, by the way. Don't feel like you'd have to show this much work every time. So we're going to go ahead and take our Ba and our C, put 2 plus, 4 minus, cross our charges. You would get Ba4, C2. Now there was one other note on that last section in the notes that said this also needed to be the simplest ratio. We had to make sure it was reduced as far as it could go. In this case, 4 BAs and 2 Cs would balance out. 4 times 2 is +8. 2 times -4 is -8. +8 and -8 completely cancel out. But we could lower this ratio. Both of these numbers are divisible by 2. So we're actually going to divide them both by 2. And that will give us Ba2C, and this would be a C1, but we don't actually write the Roman numeral 1. The fact that this C is there at all tells us that there must be at least 1 carbon. The fact that there's no number there tells us that there is only 1 carbon. All right, then we're going to take our ionic compound, and we're going to name it. So the first thing we do is name the first piece. The first piece is barium. Leave a gap in case we need it. The second piece is carbon, but we change the ending, so it's going to be carbide. And then we ask, is barium a transition metal in the lower P block or in the F block? And the answer is no. So we don't actually need any Roman numerals on this one. And in fact, you would be counted wrong if you put a Roman numeral on that one, because again, you only do that for those elements that are in this lower area right here, the D block, or F block. Okay, these next examples get a little bit tougher. We've got silver 1 and sulfate. And the reason they get a little bit tougher, let me pull out my camera a little bit more. is because silver 1 is easy. It's Ag with a 1 plus charge. Now, I didn't need to put this Roman numeral 1 there because silver is always plus 1. But I'm being nice because this is an example problem, so I made sure to actually give you that. But sulfate, if you look and look and look and look and look on the periodic table, you will find sulfur, but you will never find a sulfate. And that is because sulfate is a polyatomic ion. Now, you should have these memorized, but if you don't, sulfate is right here. It's an SO4, and it's got a 2 minus charge. So we're going to keep that whole piece, this whole SO4 with a 2 minus charge, all stays clustered together. It is one compound, or one chunk of atoms that is going to stick together in this compound. We treat it like it's a single atom. So now we're going to bring those two pieces over here. I've got Ag1, SO4, 2, cross our charges. We'll get Ag2, and then our SO4 does not get a number. Now, if there was a number, which we'll see in the next example, we would have to start using things like parentheses. But for this one, we don't need to do anything. We'll just leave it at that. And then for our naming, because this can't be reduced, we would name the first piece is silver. We would name the second piece. Now, this last time we changed the ending to IDE, but sulfate is a polyatomic, so we do not change the ending. We're just going to leave it as sulfate. And then add a Roman numeral if you need it. Technically, you don't, but if you wanted to add one to this, I would not count off against you because it is technically in the D block, but it doesn't need one. So I'm going to put a very lightly with my pencil here. I will put my Roman numeral 1. Very, very, very lightly. Okay, last example. We've got calcium phosphate. Calcium is Ca. Ca on our periodic table is right here. So that's going to be a 2 plus charge. Phosphate, again, you're going to look and look and look. You may find phosphorus, but you won't find phosphate. That 8 ending is reserved for polyatomics. So that's a good sign that you're dealing with a polyatomic there. So instead, we have to look at our other sheet, or hopefully have them memorized. We'll get PO4 with a 3 minus charge. So we're going to take Ca. We're going to take PO4 with a 3 minus. We're going to cross our charges. Now, this is where it gets a little bit tricky because our Ca3 is easy, but like I mentioned up here for our Ag2SO4, we could leave this alone because there wasn't a number. Your instinct might be, okay, well, I multiply this by 2, so it'd be like P2O8, but you do not do that. The unit that is repeated over and over again is a PO4. It is one chunk of PO4, and then there would be 2 of those PO4s that would be attached to this. So it's actually going to look like this. We're going to put our polyatomic in parentheses, and then we're going to put our number outside of the parentheses. So 3 and 2 can't be reduced, so we don't need to do any reduction or anything like that. That's in its simplest form. So then we just name it. Naming it would be calcium, leave a gap, phosphate. Calcium does not need a Roman numeral because it is in this part of the table. We know it always has the same charge, so we don't put a Roman numeral when we get calcium phosphate. All right, while I'm doing this video, I am going to go over, and we're going to do actually one other set of examples because I realize I have problems that are like this on the notes, but I don't have one worked out as an example in the notes. So I wanna work one out now. So we're gonna do, we'll do 2 separate extra examples here, 2 separate extra types of examples. So we're gonna go MO. MOS. M-O-S. And then we're also going to do, I'll do over here, we'll do We'll do an easier one. We'll do Ca3N2. Now, the difference in these are that we are going from the actual formula to the name. The last ones, I gave you the pieces. You combine them together, and then you could kind of just use the pieces from earlier to actually solve them out. We're going to start with the easier one, which is the one I did on the right. So we're going to look at these pieces here, and we're going to split them apart, and we're going to figure out what are the two pieces involved in this. Well, Ca is calcium, and N is nitrogen. And once you've identified the two pieces, you kind of ask yourself those same questions that we just did in reverse. This is calcium, that's our metal, so that's going to stay the same. We can go ahead and bring that down. This is nitrogen, but we've been modifying the ending if it's not a polyatomic, and N2 is not a polyatomic, so that means it must be nitride. Again, IDE is used pretty much exclusively for if something is a single element, the only exception being cyanide, hydroxide, and peroxide. Everything else that ends in IDE is a single element. And then you ask yourself, does calcium need a Roman numeral to let me know what its charge is? And the answer is no, it doesn't. Calcium is just a normal element. It doesn't it isn't in the P block, the D block, or the F block. So calcium nitride would be the name for that one. Now, as you might have guessed, based on me doing that one first and this one being over here, but it being the first one I wrote, I wanted to make sure that we had one where you would have to do a little bit more work. So we've got MO and we've got S. MO is molybdenum, because I hate myself and apparently want to make a really long word that I have to write and try to remember to spell correctly. And then S is sulfur. So what would be the name? Well, we would have molybdenum, leave a gap, sulfur becomes sulfide. And then our next question is, does molybdenum need a Roman numeral? And if we look for molybdenum on the periodic table, you would find that it is right here, which means yes, it does in fact need a Roman numeral. So since it needs a Roman numeral, we now have to figure out what its charge is. In all the other examples, we were told what the charge was. Now we have to do a little bit of detective work, and we have to be able to figure out what the charge is. So here's how we're going to determine what the charge is. First, you need to identify what sulfur's charge is. And looking at the periodic table, sulfur has a charge of 2-. So if sulfur has a charge of 2-, you then have to go through and kind of ask yourself logically, if sulfur has a -2 charge, what charge would 1 molybdenum need to have so that it canceled out 1 sulfur? And in this case, well, there's a -2 and there's only one of them. That means a molybdenum must have had a +2, which means we would give it a Roman numeral 2 in that question. You have to be careful because a lot of people's first instincts, like let's say we were looking at like I don't want to work out a specific example because it might make you think that it only works for that case, but you cannot just uncross your charges because notice this was an invisible number 1 down here and this was an invisible number 1 down here. So if you tried to uncross your charges and just kind of do the whole process backwards, you would end up with the wrong answer. You have to remember that there was that simplification step. So if you need to figure out what the charge of this is, figure out what the charge of this thing is. If it's the same number that's down here, congratulations, you do get to uncross your charges. But if it's not, you're going to have to actually do a little bit of critical thinking and try to solve for whatever that unknown piece is. Hopefully that makes sense to everybody. If you have any questions, please feel free to send me an email. I hope this video helps you out. It's a little bit of a tricky concept, but I do want to also warn you right now that like for this chapter, each individual piece is not that hard. The hard part of this chapter is going to come at the end when we combine every lesson we've talked about together, and you have to start figuring out not just what the answers to them are, but you have to decide, is this thing ionic, covalent, or as we're going to talk about, an acid? Because there's actually going to be 3 types of things that we're going to learn how to name this chapter. Anyway, This has been Mr. Diamond signing off. Have a good rest of your day, everybody.